Hello and welcome to this first and probably last episode of Professor Paul Explains the World, with lots of fun and smiling faces, and we dig right in with a Christmas special today here that carries the title Symmetries and the Standard Model. Now, if that sounds a bit confusing to you, don't worry, I'll do my best over the next, couple of hours to get across what we physicists mean when we say these kinds of words. And don't worry, further on, there'll be no equations involved, nothing of that sort. The whole purpose of this is really to get across the main conceptual ideas that people came up with over the, last 150 years maybe, that allows us to come up with one of the most accurate models of what we hope goes on what we believe goes on at the fundamental level that governs all these kinds of interactions that we see even around us, although that's quite a leap in between. Yes, so that's the point of this talk, is getting these basic ideas such as symmetries across, and the menu today will consist of 4 simple points. First, I'll talk about the standard model, because obviously that's something I should introduce if I want to talk about it, and the same applies to symmetries, both stuff in the title. I'll introduce the two separately, I'll mix them together, see what comes out. Then I'll talk about symmetry breaking, which is another very important concept in particle physics. And finally, we have to make sure that there's lots of fun time. Hell yeah, very nice. Great, so let's kick right in. What is the standard model? The standard model is a theory, and it is the most successful canonical theory of particle interactions, of the physics at the fundamental scale. It is easiest to teach as in being just a model about particles and their interactions. It actually is a field theory, but I won't go into this. Just not making this too complicated in the beginning. We have a theory, and there are lots of theories around. Science is full of theories, and even outside science, we have lots of theories about why the milk disperses in my cup here the way it does, why animals develop the way they do, why our brains function the way they do, and so on and so forth. And the standard model is just one particular of them. It's just very successful, and it is quite fundamental in the sense that quite a lot of processes in other theories we may hope to be just special cases or macroscopic results of the kinds of things that are being described by the standard model. So, without making this too complicated, let's think of the standard model as just being a theory about particles and the way they interact. I would have written this down while I was talking, I just won't. So the question, obviously, to ask is, what particles? Well, basically, the standard model distinguishes between 2 kinds of particles, one of which, roughly speaking, constitutes matter, and that's really, if we look down here, we have the model of an atom, which I hope most of us have still seen from high school. So we have, let me just pick a good color here. We've seen the core in the middle, and then the thing down here. Forgot how it's called. So in the middle we have protons and neutrons. So this is a positive proton. This is a neutral neutron. There's a negative electron that, cruises around the nucleus at some distance, and these are all particles that appear in the Standard Model, and basically, we know that protons and neutrons, together with electrons, make up atoms, which then form molecules, which then form all kinds of compounds and stuff from which matter is being made. And the Standard Model goes even further in that it splits up these elements, these particles, the neutron and the proton in the core, into the little children down here, which we call the quarks, and add some other things to that. But that's basically the one category of particle that we have in the Standard Model, all those particles which end up constituting matter. And then there's the second, which basically are particles that carry forces. So all the forces that are exchanged between these kinds of particles, but also between the force particles themselves, are being carried by force particles. So I just want to stress that principal distinction between particles that constitute matter, roughly speaking, and then particles that carry forces. Where there's another nice diagram here. So we have these two atoms, but they kind of repel each other, they attract each other, and there's other forces kicking in, and all these kinds of red arrows would effectively be what we think of as being force particles. Well, if that was it, that's basically the Standard Model in a nutshell. But it's not really the Standard Model. It's well, in any case, let's not go into here. One important thing to say at this point, without introducing any names, is that these two, what the difference between these two particles, namely the ones that constitute matter and the ones that carry forces, is that matter particles can never be in exactly the same state. So the closer you bring them to another, even just in space, if I had two of these matter particles in one on my left and one on my right hand, and I tried and bring them together, there'd be more and more of an effect of a resistance towards bringing them into the same state. If I had two of them of the same kind and I try and put them together, then we get these red arrows here that try and push them away from each other. And that's really important, and that we think that kind of intuitively makes sense for that kind of property to constitute matter or structure, to lead to structure, because the reason that, for example, when I hit this table and I can't just my hand won't just go through it, is simply because on my finger there are lots of these kinds of matter particles, and on the table, this table is made up of all these kinds of particles as well. So trying to push my hand through would involve bringing lots of these particles basically into exactly the same position. And it's that really basic principle. Matter particles will never be in exactly the same state, that leads to what I experience as being the resistance of the table against me going through it. So it's a very simple thing, but it leads to this kind of structuredness that we find, in matter, obviously. And importantly, for the particles that carry forces, this is not the case. Force particles can be in the same state, but that's just something very important we found in the 20th century, and it's really at the origin. Well, it's a corollary of what is at the origin of making that distinction between matter particles and force particles. But I see I'm already having difficulties not being too complicated about these things. So that's about the matter. Let's just think about matter as being particles that will never occupy the exact same state. And then there's the force particles. Now, what forces does the Standard Model involve? Basically, the Standard Model, the way it works so far, distinguishes between four fundamental forces. First of all, there's electromagnetism, basically anything that is charged, such as the proton and the electron will interact via the electromagnetic force. There's gravity, what keeps us from floating around in space, but just keeps us on firm ground, and also what makes the Earth revolve around the Sun, and the Sun revolve around the center of the galaxy, and the galaxy to revolve around the center of some cluster of galaxies, and so on and so forth. So it's really, really important. Both of them are really important forces. And then there's two other forces that are not so evident, at least at our scale, but they are really important. One of them is the weak force, which is responsible for radioactive processes. So if we think of Fukushima, there's lots of weak force action involved there. It's also very important in keeping the sun, for example, from fueling out all too quickly. Well, as it says, the weak force happens very well, comparably, not slowly, weakly. Weakly, I think, is a good word for that. And then there's the strong force, which basically keeps the quarks together so that they form protons and neutrons and all other kinds of particles that you can build up from these quarks. Now, I haven't maybe made clear enough yet that distinction. So what I want to get at here is that we have these matter particles. There's a couple of them, and for each of them we can ask what forces is it sensitive to. So some of them just won't feel certain forces when they do others. So by looking at what combinations of forces certain matter particles are sensitive to, we can characterize these particles by that. So I said, for example, electromagnetism involves anything that's charged. So electrons in protons, they feel electromagnetic force, whereas neutral particles just don't. They just go through the world completely ignorant of that electromagnetic force even being there. And same is true for gravity. So gravity works with mass. Mass is the important property that determines whether a particle feels gravity or not. So massless particles will just not be subject to gravity, and so on for weak and strong force in a more complicated way. And I said to each of these correspond particles. So these forces are not just acting over a distance or something, but we believe there to be particles that jump, so to speak, between matter particles and effect that transmission of force. So in the example of, in the case of the electromagnetic force, that is just light. Light photons are the carrier of the electromagnetic force. So we have the forces, we have the matter particles. Let me just write that down. So we have that here. So we have the standard model, which is a theory about elementary particles and their interaction via other particles. I mean, that's not one shouldn't be too tightly woven about this, just calling something a particle here, because as I think I said before, the standard model actually is the theory about fields that interact, and what people call particles are really excitations of these fields, which are in a way easier to conceptualize, easier to imagine. We have immense difficulty thinking having the mindset of a field theory, but really, that's what the Standard Model is. It's a field theory. And so, if you ask yourself questions such as, surely, if the force particles are particles as well, then what is an interaction other than just another particle? And you'd be right in thinking that, and you'd be right in assuming that there might be some conceptual problems in thinking about it in these terms, but really that conceptual difficulty does not show up in the maths, or not until you dig a bit deeper. So just anyway, we have the Standard Model, having being that theory about elementary particles and their interaction, and then we've also seen that there's these two different kinds of particles, matter particles, which don't sit in the same state. Sorry, I should have. And force particles for 4 different forces, they can be in the same state. So there's a little recap box here, didactically very valuable, but I'm not able to use it properly, I guess. So in any case, I hope you're with me so far. So we just have a theory and involves all these particles and these force particles, and so we press the red button and let go, let them go and play, and what we find is that there's this, oh my god, this massive confusing zoo of particles, all kinds of things happening. There's a sheep and giraffes and neutrinos and quarks and kaons and mesons and baryons, all these kinds of confusing particles floating around. You might have heard of the Large Hadron Collider in Geneva, in Geneva, and it just bumps all these particles together, and you get massive explosions and many particle reactions. They look a bit like this. Maybe a bit like this, and so as a physicist, you might not be so satisfied with that. You might want to say that, really, I don't quite believe that there's not a more beautiful way of bunching groups of these particles together, making sense of why they interact in the way they do, why should we have 4 forces, and so on and so forth. And these are the kinds of underlying motivations that fire research into the Standard Model and going beyond it. And what we need to say, group these together or these together, is really symmetry. That's been a major recognition in the past century, and that'll be our next topic. So what is symmetry? Well, let's have a look at this sphere. And okay, it looks like a circle. Well, I guess it is a circle, but think of it as a sphere. So same thing, just in 3 dimensions. And I take that sphere from you, and it's a perfect sphere. There's no mark on it, no little imperfections of fabrication, remnants, artifacts. And I take that from you and have it behind my back, and I maybe do something to it, flip it in my hand and give it back to you, and I ask you, do you want to bet with me? Did I rotate it in my hand, or did I just leave it there? Do you want to bet? Make a bet about it? And you really shouldn't, consider betting that with me, because you have no way of finding out if it's a perfect sphere. Then the sphere after I rotated it, I flipped it around or something, will look exactly the same as it did before. So you've no way of telling whether I did something. So you would have to rely on me telling you the truth, and that's always a bad idea. And really, that gets to grips with what symmetry is. Here's another example. You have a equilateral triangle, so all three sides are the same. It's not quite in this drawing, but just think of that way. And then I flip it by a 60 degree, and well, just looks exactly like the thing before. So could play the same game with you, and still you shouldn't bet with me about anything, because you just couldn't tell. And that's really the most general, or very general way of thinking about symmetries, is that there is a symmetry about a system, in this case about the sphere or the triangle, where if you do something to it, nothing changes. It's just as if you hadn't done anything to it, So of course, this doesn't mean that you take any system and you do any kind of thing to it, and it has to be the same. I mean, surely, for example, if I had my triangle and I flipped it around not by 60 or 120 degrees, but by, say, like 3 degrees, then surely you could have told that I'd rotated it. So it's only certain things that I do to that system, and it remains. So the symmetries can be captured in this way by saying, well, you can do 3 different things to it, and once you do it 3 times, you'll be back to where you've been, and so on and so forth. That's a big subject in maths and physics and everything. But we're now approaching the main idea of why symmetries would matter for physics, and it requires this somewhat subtle distinction between theory and the nature that theory tries to do. So, we physicists come up with theories. We don't come up with nature. And what we try to do with these theories is map. What we're trying to do is come up with theories that map onto nature in a good way, such that everything that we do in our theory corresponds to nature, whatever that is. I mean, of course, that's a delicate thing. There's a very delicate divide here. But let's just take that as a working assumption, because we're physicists and not philosophers. And so why would symmetry matter for this? Well, in theory, that's another assumption, that's not a given, but it's something we can assume, that theory, really, everything that could make sense to us, to humans, we can put into formal language, maths, for example. So anything that we can conceive of, where it's an assumption, can be translated into maths. So we can do lots and lots of things, maths. Like, we could come up with any kind of crazy universe and describe it mathematically, whereas nature is clearly characterized by the fact that you can only do some things. So you can't do anything. For example, I don't levitate just because I want to. I could easily come up with a theory in which, well, not easily, but I could have probably come up with a theory where I, just being here, just start levitating, fly around as I want, control it with my mind and everything. But our world is characterized, it seems, by the fact that we cannot. So, if we go back to our example about the sphere, there is the following state of affairs. If I rotate the sphere, we talked about this perfect sphere, and I rotate it about any angle, it'll always look the same. But still, I can mathematically, I can describe that rotation. And so, for me as a mathematician, the left-hand ball will, for example, be, I don't know, there'll be some angle here, let's call it theta, and that has some value like 0 degree. Oh no, now there's the first equation. And I flip it around, I say, oh no, now this theta is down here, so it's all this thing, and theta is changed. So now it's like, I don't know, 60 degrees. So I did something to it, and mathematically I say, well, this is a sphere with theta being 0 degrees, and this is a sphere with theta being 60 degrees. So they're not the same thing in theory. According to the theory, I've done something to it, and I can describe what I've done to it. But in nature, if I had such a perfect sphere, I wouldn't want it to matter whether theta is 0 degree or 60 degrees, because it's going to be the same object. It's going to be the same physical object. So if I rotate it, and it is perfectly symmetric, then I want it to correspond to the same. I'd want the physics derived from the theory with theta being 0, and the theoretical description of the sphere with theta being 60 degree to be exactly the same. I hope you're with me on that, because that's the main idea. It's really important. For any symmetry in nature, the predictions of a theory should not change under the symmetry, where by under the symmetry I mean, for example, in the case of the sphere, the symmetry of rotating it. So this is, again, not saying that all kinds of symmetries have to be the case for there to be any symmetry. Oh no, how can I say this better? Let me just pause here and think for a second. Okay, so we can maybe think about this in the following way. There are some symmetries in nature, by which I mean that there are certain things that you can do to stuff, to things in the world, or the universe as a whole, such that if you did that, after you did it, the universe, or whatever object you did it to that has the symmetry, looks exactly the same, just as the sphere we've had. So you can, for example, think of no, I think I'm actually having an example of that in the next slide. So maybe I should just carry on with that. If there is a symmetry of that kind, and that's true about nature, about the world, then the predictions of a theory that describes that world, for these predictions, the differences you can express in theory that describe these symmetry transformations. I was hoping to avoid that word, but the kind of things you do to the objects, such as theta being 0 or theta being 60, that really should not play into how you come up with predictions about the future behavior of these symmetric objects. Okay, let me just go to the next slide, but let's not forget that we're having loads of fun, great Christmas mood, ice cream and everything, really good. So here's the example. I have my sphere again, maybe think of it as a ball this time, a perfect ball, and I have a wall here, this thing here, that's a wall. And so I'm going to bounce the ball against the wall. Now, if that ball is perfect, then if I spin the ball around, say I did this kind of rotation to it, which I have here in the middle, and I spin it around a bit, then my theta would have changed because I spin it around a bit. But surely if that ball was perfect, I should get exactly the same behavior, the kind of predictions about what the ball is going to do once I bounce it against the wall, should be exactly the same in both cases. So whatever theta matters, whatever role theta has in the theory, it might play a role there. It's not forbidden. What is forbidden is that the physical predictions of that theory should. What is forbidden is that they should depend on the theta. So the theta should not come in there. The physics should be the same. And if we think of a second scenario, that's a bit bad now. Any case, if we think of the second scenario where there's some asymmetry, the ball's broken here, and I spin it around, then surely I wouldn't expect that to be exactly the same thing, because in this first case here, I have the ball bouncing off with this weird kind of corner here, and it'll just skew off in some random direction, whereas here, it still bounces off with that part of the ball, and you would not expect to be a problem in the first place. So if the ball is symmetric, same bouncing. If the ball is not symmetric, well, then it doesn't have to be not the same bouncing, but in general, it won't be the same bouncing. Okay? So that's really the main idea. And that creates a lot of problems. I mean, it's a basic idea. It's really, really simple in a way. But it's very difficult because, of course, the kinds of physical systems that you want to describe are much more complicated than just balls bouncing off walls. If you have all these elementary particles, you want to make sure that for whatever you believe the symmetries of nature to be, that your most general formulation of what their interactions might be and so on and so forth should predict the same physics for all of these particles, for all of the symmetries in nature, and you want to have that in a general formulation, then that creates a difficult job, although you started off with this very simple thought. And so I've been banging about these symmetries of nature. It's a bit of a misleading word, because of course conceptually the symmetries appear in the theory. Nature never knows about these symmetries, because they describe that kind of redundancy. No, I shouldn't say that word. I'm saying all these words I was really hoping not to say. I'm just going to try and make it much simpler and less rigorous. So we have these symmetries of nature. What are they? Question. The first thing to notice, after of course noticing that I've been a cruel boy and split this butterfly into two parts because I had to squeeze the heading inside, but it's kind of symmetric, is it? First thing to realize is that there's this intimate relationship between symmetry and conservation. So you might or might not remember that there's these kind of conservation laws about nature that you learn of, but in high school physics, conservation of energy, conservation of momentum, conservation of charge, and really these correspond to underlying symmetries. They're just the kind of the result. Their conservation is a result of underlying symmetry properties of the universe. So I'm gonna be more specific about this in a couple of minutes. But first of all, let's recognize this. It's kind of intuitive to think that if you have a symmetry, you'll have a conservation, because okay, how can I think about this? I'll try not to think about it now. So let's first start off with a couple of pretty intuitive kinds of symmetries we'd expect nature to have. If we take any system here, like such as a sphere, but let's say it's more symmetric, more general, so we put an S there for system, and we wanted to translate the whole system independent of its environment. There's no environment really by 5 centimeters. So we kind of translate it in that direction, as I have this arrow here, and surely if that happened, if even the whole universe was shifted by 5 centimeters, even though I don't think that's a sensible statement, then we'd expect the physics to be the same. Yeah, so that's quite a, well, you might say trivially seeming symmetry, but it is a symmetry, and your theory should take that into account. There's another one which is rotational symmetry. So if I took the whole universe and rotated that by, some angle theta again, then that should leave it all invariant as well, because there's this relationalism in play here, that we think in the end, if the standard model has all these particles, and what happens next really just depends on where the other particles are at this point in time relative to the particle whose future behavior I'm trying to predict, then if I rotate the whole thing, and these relationships, these relative positions, or whatever you want to call them, of the particles should not, they'll be the same. So therefore the physics will be the same. So I want my theory to be the same, predicting the same things if I simulated rotation globally. And then the third thing is that we've learned from special relativity, which is another theory about space and time, that really space and time are, aspects of one bigger four-dimensional space-time, such that if you describe the particle as moving, as being at rest, or you describe the particle as moving along some frame, with inertial speed, just at a constant speed, but that works even for accelerations if you do the right calculations. The physics still should be the same. They might be described differently by, depending on the speed that these systems move in, but that's the lesson we took from special relativity, and that's the kind of light cone I drew here, which I really shouldn't have. I'm making it all so complicated, I'm sorry. Is that the physics should be the same regardless of whether the whole thing is moving at a certain speed or it's just standing still. So these are 3 symmetries that I expect of nature, and we find confirmed so far, and they're global symmetries because they basically apply to the whole universe. Yeah. But then there's others as well, whose importance was not realized for some time, and those are local symmetries. Local because I apply them to only certain parts of a system. So let's think about this sphere here again, this general system, and I'm having this one point here, and I'm applying some symmetry to it, like as if I was rotating it, as if I'm doing something to it, and after doing that something, the system is the same as before. The physics, the way it will behave, is the same, and I can do that to other points at the same time in other directions. I can do that to many points. So we call that local. But I can totally see if that's really confusing, because, like we say, what the heck, because surely these kinds of symmetries could not be translations or rotations in the same way in which these global symmetries before have been. Why? Well, if you think that the physics in the universe should be the same, if I took some tiny part of it and shifted it by a couple of centimeters, but leave the rest the same, then just think about, taking all the elements, all the particles that constitute your brain, and just shift them by, lift them by 20 centimeters. Then all of a sudden you'll have problems, because your brain is out there and you're still here. It's problematic. So surely that's not the kind of thing, or you just flipped your brain upside down. That's going to be problematic as well. And the same, of course, applies to inanimate matter and everything. It's just those are not the kinds of symmetries we're talking about here. And of course, I want to give you an idea of what kinds of symmetries we're talking about. But before you can do that, you need to have a little bit of patience with me, because we're having a very short detour or discourse into degrees of freedom, what degrees of freedom are. And for that, forget everything I said about symmetry and so on. We're just having this little blue box. We're in another world now, another talk, and we're talking about degrees of freedom. I want you to imagine to play a super cool game, computer game, where you can develop your own character. So, it's a robot game, so you have this robot here. It's pretty profileless in the beginning, and you get this menu in the beginning, like you can choose what you want for the head and what for the arms and the feet. So you get options. You want a wig or a hat, so you choose a hat, and you say, wow, looks pretty cool. Or you want to try a wig. Yeah, I mean, your character certainly likes the Mozart wig more. Maybe it's that. I don't know whether that's Mozart or anyway. And you can do the same for the arms and the feet. And so if you did that, wow, you end up with a cool Mozart eagle wing ski driving character, or you end up with a vampire Pippi Longstockings with serpent arms and cow feet. Or you go really crazy and you turn to this Darth Vader, Popeye armed, femme fatale kind of figure. But the thing is that you get all these independent selections. You can choose something for your head, you can choose something for your arm, you can choose something for your feet, but you can just go and change your head without changing the arms, without changing the feet. So what I want to say is that the selection menu for head, the selection menu for arms, the selection menu for feet, each corresponds to a degree of freedom, because it's something you can do to come up with a character that leaves everything else invariant, in just the way it was, but you can choose freely from all these things. And now in that case, the wig and the hat would be specific values that your degree of freedom can take. So you have the degree of freedom hat, and you choose wig as a value, and you'd say, well, this guy right now is in the state head. Well, this guy's in the state. For the degree of freedom of head, you have Darth Vader. For the degree of freedom of arms, you have Popeye arms. And for the feet, the degree of freedom of feet, you have your femme fatale high heels. But that's all nice so far, but I think we forgot something very important about this little fella, and that's that he's got a heart as well, and a soul. He likes, and so we have this other degree of freedom here, the character degrees of freedom, and we can choose whether he's happy or sad or vain or brave, and what I'm getting at is that these degrees of freedom that correspond to the character are the internal degrees of freedom, whereas the other ones are external, in the way that if you took this whole figure, this whole guy, and rotated him around like that, of course, if you, I don't know, that makes a change in the external, in the external world or something. I mean, the guy, if you had the guy and you shoot an arrow here, I don't know, and you flip him around, then he'll be hit differently than if you hadn't done that. I mean, surely this guy does not have external symmetry in any obvious way. But it might be that you can do something to his soul, to his heart, and it leaves him invariant, and that's an internal symmetry. Well, it's a symmetry of an internal degree of freedom, and so the internal degrees of freedom correspond to the local symmetries, and the external degrees of freedom correspond to the global symmetries. So maybe I should just, where am I next? Oh yeah, no. So So maybe if I go, so this is the local thing. So each of these would be kind of like a heart or a soul of whatever system you're looking at in that system, and you change something about that, which is of course not a rotation or a translation as in these straight arrows, but something else that leaves them internally invariant, internally the same. I'm saying all these words I never want to say. I hope you're still with me. And for the very brave ones, I'm having a digression in the digression because it's just so interesting. Just cannot help but not telling you this. We've heard about these internal and external degrees of freedom, but to a scientist, often the idea, the concept of an internal degree of freedom sounds a bit awkward because it's, think of it as, well, it's more than just an analogy, but the way in which science always, strives to get rid of concepts like soul, this kind of ineffable, not ineffable, these things you can't get at scientifically with rigor. They say, well, really, soul, you outsource it into, explain it by chemical processes that take place in your body. And of course, these processes in your body are happening in the external world, so to say. They correspond to external degrees of freedom. If you wanted to specify where all the chemicals in your brain are that make you feel happy at the moment, then they'd be subject to that would be external degrees of freedom, not internal degrees of freedom. So we're constantly trying to get rid of internal degrees of freedom by explaining them with what goes on as in the external world. So the idea is that every internal degree of freedom is really just a hidden external degree of freedom, and the same really happens here as well. I can try and illustrate this with my little guest here, Mr. Sponge, who's obviously has 3 degrees of freedom if you wanted to describe him. So you'd say, well, this is the kind of the corner here. You'd need 3 different directions to specify any point on him and in him. So he's got 3 degrees of freedom in choosing where you want to tickle Mr. Sponge, and he likes that very much. But now imagine we take this corner and we fold it down here. And we take this corner and we fold it down here. So we take all kinds of points up here, these sides, and we press them onto this bottom layer. What we end up with is, well, a kind of unhappy Mr. Sponge, I'm sorry, but with a flat Mr. Sponge with only 2 remaining degrees of freedom, but he's got structure here. You see these wrinkles, these things, that kind of structure that you could describe. Of course, you wouldn't get it perfectly flat, but you get the idea. So what we have here is that we've taken 3 external degrees of freedom and we fold them together in such a way that we're left with 2 external degrees of freedom. So each of these arrows is an external degree of freedom, and 1 internal degree of freedom, which in that case would be a specification of the kind of structure we have here, these lines. Well, that's maybe not the best way of describing an internal degree of freedom, but in any case, so in a similar way, we have these theories, string theory in this case, where we start off with 10 initial external degrees of freedom, and then they fold in a way in which I did fold Mr. Sponge here, such that we're left with 4 external degrees of freedom, which correspond to the 3 spatial dimensions, and then time as the 4th dimension, and 6 internal degrees of freedom, where these 6 internal degrees of freedom are just the kind of internal degrees of freedom to which the local symmetries apply, and kind of that's how we get back to what we were talking about before. But really what goes on at the fundamental level is that we're having a 10-dimensional space-time, or at least 10-dimensional external degrees of freedom, which then in the dynamics fold. Okay, well, if you didn't get that, not so important, because it's really not essential to the overall talk. But let's recap. Oh no, let's not recap. Oh, I need to write something again. Now we've talked about symmetry, and how we can think of it as being a measure of how things remain the same even though I did something to them. For example, rotation of a sphere. And we've come across this very important idea, very, in a way, quite basic, but it has this. It means there's tremendous computational effort. There's a tremendous amount of work for people to try and come up with general frameworks to describe the world, which is simply that the physical predictions of any theory, a good theory, and a theory that we want to keep working with, should be the same under those symmetries that exist in nature. I mean, not any symmetry. As again, I mean, we're not expecting any theory to be invariant, to be the same under all kinds of symmetries. There is probably only one super trivial theory that could satisfy that. And these symmetries of nature we can think of as being both global and local. So as being symmetries that apply if we do stuff to the whole system, but even though if we do stuff to the internal degrees of freedom, so we change things only to some parts of the system. Here. Okay. Now, I told you I was going to talk about the symmetry in the standard model. We've talked about symmetries. We've quickly rushed over the standard model. So what happens if I put the two together and I press the button? Wow! Yeah! Crazy smoothie. Nice color. We find that almost all the properties of the elementary particles that I talked about in the standard model arise from symmetries, namely the kinds of symmetries I was talking about before. I made explicit the global symmetries, so we want to have the same universe. If I shift it by a couple of centimeters, I want to have it if I shift it around, or if I have it moving at continuous speed. But then there's also a couple of symmetries, internal symmetries that I won't go into now because it's going to be too complicated. But all the kinds of properties that the elementary particles have, each of them corresponds to the invariance, the being the same. It's being the same under these symmetries. As an example, if you concentrate only on the global symmetries, if I tell you that my universe has to be symmetric under these three transformations I was talking about, and, well, in a special way, so you shouldn't flip time around, and you shouldn't, that's all quite rough. I mean, you couldn't say that to physicists, but for you bunch, it's going to be enough to say that if I take any universe in which I have these kinds of global symmetries I was talking about before, then naturally you'll have properties arising, such as mass and spin of these particles. Now, you may not know what spin is, so, but you surely know what kind of mass means, I hope, I guess, I don't. and that it's just the statement that your universe is invariant. It stays the same under these 3 or 4, basic global symmetries, and already forces you in a certain way into these mass properties and the spin properties. And spin, well, it's a very important thing, and it's just mind blowing that just the statement of the global symmetries, together with a couple of technical details such as representations and this and that, blah blah blah, just naturally leads you to distinguishing mass as a property of particles. So, before I get carried away, oh yeah, I have it here. Global symmetries, mass and spin. Local symmetries explain a lot of the grouping of elementary particles, so they seem to come in groups, that, where the specific values that their properties take are somehow related, and we find that these are just the symmetries, the local symmetries, the internal degrees of freedom, the symmetries in the internal degrees of freedom that lead to that grouping of elementary particles. So that's really the most striking thing I wanted to get across, and it is difficult to understand. Far from saying that I, completely got the hang of it. It's even difficult to overestimate, I would say, because the fact that you can put a number of property values together as being corresponding to some symmetry is not in itself, I guess, too striking. But I shouldn't bang on about this. It's certainly very interesting, and it's great that only giving me the symmetries that if somebody gave me those symmetries, told me these are the symmetries which are true of nature, then I'd be very limited in the amount of specific universes I could derive from just that information. Just specifying a bunch of global and local symmetries that are true of the world extremely narrows down the kinds of universes that can be the case. And vice versa, you can also, kind of start asking these kinds of fancy questions, as in like, we see that the kinds of elementary particles we have, they're really good for coming up with stable galaxies, with stable solar systems, and stable planets, with good conditions for life. That's crazy. How come? But I'm not so interested in that. I guess, at least not ask them this way. So, that would be a good place to stop. I've almost talked for an hour. Crazy. We could be all happy and say, wow, symmetries, and we can be like Buddha here. But of course, I guess one of the pathologies of the Homo Occidentus is that we're kind of unsatisfied whatever we have, and like Napoleon here, we want more and more and more, because that's just the way we are. And of course, science is a child of that kind of mentality rather than that kind of mentality. So what we want is even nicer. We want even less forces, and we want even less particles, and nicer symmetries. And the way that this works, and this is called unification, this idea, is that we think, the 4 forces we have, they're not fundamental enough. We want one fundamental force, and all these kinds of particles, the whole bunch, we want it to be like just tiny bits of them. And well, unification, I guess the name says it also. In the case of the fundamental forces, this is how people imagine that to be the case. We think that certainly nowadays here, we have these 4 different forces, and they do very different things. There's no way of just blindfolding yourself and saying, well, actually, they're just one force. I mean, obviously not. They do their own job, and different particles interact with different kinds of forces. Remember what I said earlier about the strong force being responsible for kind of keeping quarks together to form nuclei, and for atoms, electromagnetism doing something very different, gravity definitely doing something very different. So there's no way of neglecting that we have these four distinct forces. But we can say, well, this is we're really in one specific point in time, and we have very specific conditions here, and we believe that there's been this Big Bang, and that if we go back, I'm just trying to draw something. If we go back in time, it gets hotter and hotter. So we have here the temperature of the universe, and we have down here. Hope you can. I don't know whether you, I don't know whether you can see it, but there's the time in seconds down here after the Big Bang. So 10 to the, now we have 10 to the 17 seconds since the Big Bang. It's a massive amount of time, but really just shortly after the Big Bang, 10 to the minus 43 seconds. I mean, that's 43. So it's 0.000 for 43 times, and then it's a 1, or maybe 42. I don't always mix this up. And so it's a crazy short amount of time, 10 to the minus 35. Still really short, but of course there's a big difference between these two times and these two times again. The idea is that the closer we get to the Big Bang, the more these four different forces actually end up as being one. So at this point here we have electromagnetism and the weak force turning out to be the same force. Then we have all three, the strong, the electromagnetism, and the weak force being one. And then here, just at 10 to the minus 43 seconds after the Big Bang, basically we have gravity splitting off. So at the very short amount of time, that still has been very important. I won't go into the cosmology. Before that, we have this one fundamental force, and together with unifying the forces, of course, distinguishing between different particles also makes less and less sense, because I need to have these four different forces to say, like, oh, how does that one particle interact with the strong force, or the electromagnetic force, or the weak force? Because, I mean, I need those four to be asking these questions. If I ask that question here, I could only be asking, oh, how does it interact with that one big force, which unifies the strong, the weak, and electromagnetic force, and gravity. So there's only two questions to ask. So the less forces it could theoretically interact with, the less properties I can ascribe to that particle. So the more we unify these forces, the more we have to treat what now appear to be different particles as being the same particle. So we want to unify both forces and particles, and that's the underlying idea. Now, you might think, guess already, so why am I saying this? Well, because symmetry brings us, gets us somewhere. Symmetry considerations get us to come up with a theory of how that might be happening. And to understand that, we'll have a quick run through symmetry breaking. No worries, we're almost at the end. So you remember that was the last of my points on the menu, apart from fun. So symmetry breaking, let's think back of our sphere here. We can say, well, we can rotate it in these two different directions, and any kind of rotation can be basically split up in some rotation around this axis here. Why is it not working? This axis here. Well, it's not working. Oh yeah, now it's working. This axis here, still not working. Whatever. This axis here, and then this axis there. So these two degrees of freedom that I have in rotating the sphere. And imagine I turn a point here. Then surely, under all kinds of general rotations, that point would be somewhere else. And I could easily tell whether or not that sphere has been flipped, rotated. You know, if you gave me, if I took that ball from you with a dot on it, and I had it behind my back, and I gave it back to you, you could say, well, either you could easily tell whether I did something to it. If the spot's still at the same place, you could say, well, maybe you flipped it around by 360 degree, like just the whole turn, or you did that twice, or 3 times, or 4 times. But if that was not part of the rules, if I could only do it maximally by just below 2 turns, and then you could immediately tell whether I did something to the ball just by inspecting the position of the dot. So you could say, well, surely that's a kind of symmetry breaking, because I used to have symmetry there, now I don't. But now, let's think of the following. Say I have the dot on the South Pole, just on the bottom part, on the most, I just have it in my hand, and you dot it, put the dot on the very bottom part. Then, if I rotated the ball around the axis, the north-south axis, that goes right through that dot, then you can imagine that I could still, that's kind of rotation I could have done to the ball behind my back, and the ball would have not, that's something you couldn't have seen. So there's this one rotation, namely around the axis, that spikes through wherever the dot is, that still leaves the sphere invariant. So in that sense, you would still lose a bet against me if we were betting around whether or not you can find the difference or not, because I just always rotate it around this axis, and then you couldn't tell whether I turned it around by 0 degrees or 30 degrees or whatever. So what's important here is that we started off with 2. So the initial ball could have been rotated around any of the 2 directions I was pointing at here. So we have 2 directions, and after dotting, we still have a symmetry, but we have a symmetry of only 1 degree of freedom. There's only one specific rotational axis by which you can rotate it, where before you could have chosen basically any, but could have been split up into these 2 rotations here. So we go from 2 degrees of freedom to 1 degree of freedom, or 2-dimensional symmetry to 1-dimensional symmetry. And that is the basic idea, that the symmetries that led to the standard model, the symmetries that we've been talking about, the global and local symmetries, particularly the local symmetries, those are actually broken symmetries. Alright? So they're not, so we have, okay, let's just go on. So we go back to force diagram, the sketch of it that I've been showing you. So here is now, and so we have these 4 forces, strong, weak, and gravity. But these are still the result. A description of them is still the result of these symmetries that I spent over an hour now talking about. But really, what happened is that we started off at time 0, at the Big Bang, with this undotted sphere. And then when the first force split off, what happened is that there was this kind of dotting. So we broke a symmetry, and we came from some number of degrees of freedom to less degrees of freedom, but there's still the symmetry by this axis here that I was talking about. So the second one would have been another dotting and another dotting. So after 3 symmetry breakings, we end up with 4 different forces, but they're all really different facets of being that one unbroken symmetry. Of course, that completely doesn't work with the specific example of the sphere, because the sphere, we started off with 2 degrees of freedom, and so there was only 2 steps I could have taken from 2 to 1 to 0. So in this case, there surely wouldn't have been any symmetry, because I couldn't have. As soon as I have 2 dots on the sphere, there's nothing I can do without the change being obvious. But of course, the dimensions, the degrees of freedom, the numbers here that we are talking about in the unification model, and even in the standard model here, are much higher dimensions. That's just to show you how the analog works. So yeah, just to stress that this kind of sphere here would correspond to the standard model symmetries we have so far, because the standard model, what it does, it unifies. Oh no, actually that's wrong. It should be this one. What the standard model unifies is these 3 forces: electromagnetism, weak, and the strong interacting force. So we've made it all the way up to here so far with our theoretic description. It works beautifully well, but gravity still kind of stands out, and there's been lots of attempts to incorporate gravity, and there's been also attempts just to show that how can I say this? We have a well-working kind of symmetry that explains all these things, but it's not the most beautiful symmetry. It's not one big symmetry. It's a product of several different symmetries that kind of act independently of another. So no, that's too complicated. There's 2 different research endeavors. The one is to come up with a mechanism that would allow us to show that gravity itself is the result of a symmetry breaking of this one group here, which we really want to find out. But there's this other one in that we want to find out how exactly the symmetry breaks, because there's not just one way for the symmetry to break down. If we go to high dimensions, there's several of them, and we found, conceivably unelegant ways for example, deriving the symmetries of the electromagnetic and the weak force from unbroken symmetry groups here. But we still think that if we came up with a more elegant way of formalizing this symmetry group here, then the kind of splitting that the symmetry breaking would cause could seem more natural. But so here we're talking at the forefront of theoretical physics research. Some of the names I've mentioned before is string theory, supersymmetry. Supersymmetry studies the symmetry before the 2 basic kinds of particles I was talking about in the standard model, the ones that constitute matter and the ones that constitute forces. The kind of symmetry, the supersymmetry at which they are the same, and the distinction between them being the result of the supersymmetry breaking with ground unification theory and these kinds of things. But I'll leave it at that. I hope I could get across how symmetries and symmetry considerations mash well with the outcome of finding an economical description. With the endeavor, the research program of finding an economical way of describing the kind of elementary processes that certainly govern the stuff at the elementary level, but of which reductionists, like most physicists are, believe that in principle they could be held responsible for all kinds of interactions, even at the macroscopic scale. For example, why I've been explaining all these things so much more complicated than I was intending to. Yes, I hope you liked that, and Merry Christmas and blah blah blah, all that stuff.